Hello, everybody. I'm Ran Raz from Princeton University. It's great to have Professor Cynthia Dwork from Harvard speaking today. She will be talking about the mathematics of differential privacy. Cynthia actually started the field of differential privacy and is the leading researcher in this field ever since. And this has huge impact on today's world. And it's rare to have someone who started so many research areas like Cynthia, so original. She has works on fairness in machine learning. She actually started talking about proof of work much before cryptocurrencies. She invented non-malleable cryptography, and she started with lattice-based cryptography, which is now the basis for lots of post-quantum cryptography, and this together with many other works in cryptography and complexity and other fields. So it's great to have Cynthia talking today.
Hello, I'm Cynthia Dwork. A statistic is a quantity computed from a sample. The fundamental law of information reconstruction tells us that overly accurate estimates of too many statistics completely destroys the privacy of the sample. This is true whether the statistics are requested one at a time or are stated in advance. This is the backdrop against which any theory of privacy-preserving data analysis must operate. Now, a statistic is supposed to tell us about the population as a whole. This is why the field of statistics works. The choice of the sample should be irrelevant, provided proper sampling procedures are followed. And the sense of privacy is derived from this fact. So nobody knows I need a sample. I could claim I opted out. The same things would be learned even if an entirely different sample were being used. In this sense, what's learned is not about me. So this intuition is excellent, but it needs some help, and differential privacy provides this help. In fact, differential privacy preserves the semantics of I could have opted out for every computation, including total population counts where there is no sampling. We abstract the problem as follows. A data analyst interacts with the data set. The analyst asks questions or poses studies or interacts, and answers are provided. The procedure is adaptive, meaning that the ith study could depend on the outcomes of the first I-1 studies, or the ith question could depend on the outcomes from the first I-1 questions. And the view here is that it is the data set against the world. And the data analyst could in fact be several different analysts, all analyzing the same data set or overlapping data sets, and they may be coordinating arbitrarily. And the requirement is to maintain privacy regardless. To define differential privacy, we need to introduce the notion of adjacent data sets. And these are just data sets that are almost identical, except that they differ in the data of just one person. Differentially private algorithms are randomized, which means when they're running on a database X, there will be a probability distribution on outcomes, which we denote M of X. Also, there is a parameter, epsilon, that governs the privacy loss. We'll define privacy loss rigorously later, but for now, the right understanding is that a small epsilon means small privacy loss and a large epsilon is more relaxed. So an algorithm, M, gives epsilon differential privacy if for every pair of adjacent data sets, X and Y, and all possible outcome events S, the probability that we observe S when we're running on X is at most e to the epsilon times the probability that we observe S when we're running on Y. Or another way of thinking about this is that the ratio of these two probabilities is always bounded by e to the epsilon. Note also that this definition is completely symmetric in X and Y, so we have the opposite requirement as well. And so not only is the ratio bounded, but the inverse of the ratio is bounded as well. And here our probabilities, epsilon is our privacy loss bound. It's a cap on the privacy loss. It's part of the algorithm. It's a parameter to the algorithm. And the probabilities are over the coins flipped by the algorithm. It's not difficult to see that if M1 is epsilon 1 differentially private and M2 is epsilon 2 differentially private, then their composition, where we run M1 on X and publish the result, and then M2 on X and publish the result, and we look at this as a string and as a whole, their composition is epsilon 1 plus epsilon 2 differentially private. And this is true even if the second algorithm, the choice of the second algorithm, is made adaptively as a function of what was observed in the outcome from the first algorithm. There are many interesting properties that are useful that flow from the definition of differential privacy, but two of them are really key. And these will hold independent of the choice of actual algorithm. The first one we've seen, it's closure under composition, and it says that at worst the epsilons add up. And the second is what we call being closed under post-processing, or making the algorithms are future-proof. What this says is that if an algorithm is epsilon differentially private, then no new information, even detailed information about people in the data set, and no amount of computation can ever ex post facto destroy the privacy guarantee. The closure under composition property is absolutely crucial, and it tells us that we can build complex differentially private analyses from small differentially private building blocks. So our first differentially private algorithm will be the so-called Laplace mechanism. The Laplace distribution, pictured here with parameter b, has mean zero, and the probability density at any point z is exponential in minus the magnitude of z divided by the parameter b, all divided by 2b. So let f be any algorithm that maps data sets to k-dimensional Euclidean space. Our first theorem says that the following algorithm, which is called the Laplace mechanism, is epsilon differentially private. So first we have to define a notion, which is the sensitivity of the algorithm, the sensitivity of the function f. This is the maximum over all possible pairs of adjacent data sets of f of x minus f of y in L1 norm. That is to say, it's the maximum amount by which any individual can change the outcome of the function. So the Laplace mechanism says to safely output f of x, first compute f of x, and then add to each of the k components of the outcome an independent draw from the Laplace distribution that has parameter sensitivity divided by epsilon. Notice smaller epsilon will mean bigger noise, larger sensitivity means bigger noise. Okay. Now, the key to proving that this is differentially private is to look at the probability distributions on outcomes when the data set is y, and that's shown in red, versus when the data set is x, and that's shown in black. Now, if we look at any possible outcome, say t, and we look at the ratio of the probability or density that function in these two distributions at t, then by plugging in the definition of the density functions, we get that the ratio of the heights of these 2 points is always bounded by e to the epsilon. And this is true for every possible outcome t. And we call this the bounded ratio condition, and that's differentially private. Okay. In terms of accuracy, think about a counting query. A counting query says how many people in the data set satisfy some property P. Well, the sensitivity, so for this example, then K would be equal to 1. We're asking a single counting query. And so it's a real valued answer. The sensitivity is 1 because my presence or absence can change the answer to this query by at most 1. And we're adding noise now that's scaled to 1 over epsilon. And the properties of the Laplace distribution tell us that with high probability, this error that we introduce is going to look something like 1 over epsilon. And the same thing is actually true even for the histogram query. So the histogram query is a query where we take the space and we partition it into cells. And we are asking how many people in the database live in each of these cells. So if we have many cells, say k of them, that can seem like it is k different queries. But the sensitivity of a histogram query is only 1 because adding or deleting a single person can change the count of only 1 cell, and that count can only go up or down by 1. On the other hand, if we ask k arbitrary counting queries, how many people in the data set are over 6 feet tall, how many people in the data set like to play basketball, how many people in the data set like to play the violin, and so on, one person might affect that collection of k queries by k. That is, they can affect each of those counts by 1, and there are k of them, and the L1 sensitivity of that is k. So for k counting queries, these things look like k, or k over epsilon. Now, very, very high levels of composition is the reality of data use. So for example, the Census Bureau published billions, tens of billions of statistics on the data of maybe 300 million people. So the way that we cope with this is twofold. There are 2 ways. One is by relaxing the definitions of privacy. Differential privacy is a very strong demand, and so we can relax it a bit. The other is algorithmic. So one is definitional, the other is algorithmic, and we'll say a little bit about both. Okay. First relaxation is approximate differential privacy. And essentially, it just allows this small additional delta in the constraint for differential privacy. So it allows the bounded ratio guarantee. Another way of looking at it is that it allows the bounded ratio guarantee to fail with some small probability. We think of delta as being very small, preferably cryptographically small, and certainly smaller than 1 over n squared. The key notion moving forward is that of the privacy loss random variable. So consider adjacent data sets X and Y and run algorithm M on data set X, essentially drawing psi from the distribution M of X. Then the privacy loss of psi on data set X with respect to adjacent data set Y is defined to be the log of the probability or the density function, probability of seeing psi when the database is X versus when the data set is Y. Now, this is not a symmetric definition. And if psi is more likely when we're running on X than it is on Y, this will be positive, and otherwise it'll be negative. Epsilon differential privacy ensures that the privacy loss random variable, and this is a random variable because the mechanism is randomized, that the privacy loss random variable will always be bounded in magnitude by epsilon. On the other hand, epsilon delta differential privacy morally tells us, more or less, that the magnitude of the privacy loss random variable will be bounded by epsilon with probability at least 1 minus delta. Now, privacy loss, again, can be positive or negative. And when we see that, we realize that there is an opportunity for cancellation in privacy loss if we run many different executions or many different differentially private algorithms. And that brings us to the advanced composition theorem. So I'm going to start by stating the theorem, or describing the theorem for pure differentially private algorithms, not relaxed ones, and then we'll talk about the relaxation. So, suppose we have, the theorem says that the k-fold composition of epsilon differentially private algorithms satisfies the following guarantees simultaneously for every delta. The composition is, the second parameter is going to be delta for the approximation. The first parameter is k epsilon squared plus the square root of k times log 1 over delta times epsilon. So think that epsilon is small. Think of when epsilon is small. So this k epsilon squared term could be quite small. And we can actually choose things to equate these two terms. When we do that, we get a loss that looks more or less like square root of k times epsilon, rather than the k times epsilon that we got with simple composition, where we said the epsilons just add up. Now, the proof of this theorem is in two steps. For each epsilon differentially private algorithm, we prove that the expected loss is bounded by epsilon squared. And then because each algorithm itself is epsilon differentially private, the magnitude of the privacy loss is always bounded by epsilon. And so it turns out that the cumulative privacy loss is a martingale, and we can apply the Azuma-Hufting bounds, and we get a statement that sort of looks like this form, that for every t, the probability that we are t standard deviations beyond the expectation is bounded by e to the minus t squared over 2. Now, a similar statement holds if we started with epsilon delta prime differentially private algorithms instead of pure differentially private algorithms, but the proof is much more subtle. Now, the definition of approximate differential privacy, in addition to giving us the advanced composition theorem, also lets us add Gaussian rather than Laplace noise. And this is true even though the addition of Gaussian noise does not satisfy that bounded ratio condition that addition of Laplace noise does satisfy. So the form of the result that we're going to get is more or less the same. We're going to be adding noise that's somehow scaled to the sensitivity over epsilon. This time, though, the sensitivity, the right notion of sensitivity turns out to be the L2 difference. So the maximum over all adjacent x and y of f of x minus f of y in L2 norm. And the Gaussian mechanism is compute f of x. And then for each of the outcome coordinates, we have an independent draw from the Gaussian with variance sigma squared. So sigma squared looks like delta f over epsilon squared, but there's this one extra term c here, which we'll now face. So if we do this, then we get epsilon delta differential privacy whenever c squared is at least 2 times the log of 2 over delta. Okay. So we fatten it up a little bit beyond the simple delta f over epsilon, and we get epsilon delta differential privacy. So in terms of accuracy, this is great. For k counting queries, the noise is now scaling with square root of k, the sensitivity here, times c. But still, it could be a big win. But let's look at this a little more carefully. Let's fix an adjacent x and y and let psi be drawn according to m of x. Then for this algorithm, it really is the case that with probability at least 1 minus delta over choice of psi, we're going to have that the magnitude of the privacy loss is bounded by epsilon. But what happens if we're far enough out on the tail in our draw from the Gaussian, and we're not bounded by epsilon? Well, the most likely scenario is that we're actually bounded by 2 epsilon. And if that fails, again, the more likely scenario is that we're going to be bounded by 3 epsilon. And in fact, the privacy loss random variable for the Gaussian mechanism is itself Gaussian. And this is true even if we were to set C equal to 1 and just ignore that. And so we're just operating with sigma squared as delta F over epsilon squared. And when we do that, if we just throw away the ln 1 over delta term, we end up with an algorithm in which the probability that the magnitude of that the privacy loss exceeds k times epsilon is about 1 over k e to the minus k squared over 2. So it's falling off exponentially in k squared. And this then suggests an optimization. Rather than insisting that with high probability the privacy loss be bounded by epsilon, maybe this kind of a guarantee is good enough. And that led to the definition of looking at algorithms with sub-Gaussian privacy loss as a kind of first-order object. And this leads us to so-called concentrated differential privacy, which informally just says that the privacy loss random variable is sub-Gaussian. And this includes all of the pure differentially private mechanisms, but also others, including the Gaussian mechanism. If we go this route and we focus on the very high level of composition scenario, it turns out we can have more accurate analyses, for example, omitting the ln 1 over delta term in the Gaussian mechanism. But when we look at the cumulative privacy loss, we're no worse off than we were when we were being a bit more cautious at every round. And so looking at things this way allows us to cut corners in just the right way so that nothing is really lost over when we have high levels of composition. Now, a slight relaxation of this, but with exactly the same spirit, was suggested after CDP by Bunn and Steinke, and in their variant, one way of looking at their variant is as a statement about Rényi divergences. So they have a guarantee on the Rényi divergence, on the alpha Rényi divergence for every alpha. And here rho is a parameter of the algorithm, just as epsilon is a parameter in ordinary differential privacy. Okay. And this is the version that was used in the 2020 decennial census for disclosure avoidance. Okay. So that's all I'm going to say here about variance. Now let's look at some of the amplification techniques. The first amplification technique is called amplification via subsampling. So suppose we have an algorithm A, which is differentially private, and it maps data sets to some arbitrary range. We're going to take A, but we're going to modify it. So we're going to create a new data set, Z, which is obtained by, for each element X that was an input to A, we're going to randomly include Xi and Z with probability alpha independently. Once we have Z, we will run algorithm A on Z and publish the result. So the theorem says that the resulting algorithm is A e to the epsilon minus 1 differentially private. So in particular, when epsilon is small, this will give us 2 alpha epsilon differential privacy. But remember, alpha is our choice. It's a parameter. And so we can make alpha quite small, and this will result in significant reduction in privacy loss. A key aspect here is secrecy of the sample. And the intuition for the proof goes something like this. Think about an element xi. So xi will only suffer privacy loss if the intuition is that it will only suffer privacy loss if it is retained and put into Z. Otherwise, the output has nothing to do with xi whatsoever. And it's only put into Z with probability alpha. So that looks like it's giving us a probability loss of alpha epsilon for xi. But I was a little fast and loose, and this is why we have this more complicated bound. And again, this crucially relies on secrecy of the sample. Now, let's see an application of privacy amplification by sampling. Gradient descent refers to a large class of minimization algorithms that share the same general structure. To find a possibly local minimum of a function f, we're going to start at some point. We're going to compute a gradient of the function at this point. And that's usually in the context of machine learning done by summing up some little loss functions, the gradients of little loss functions at each element xi in the data set. And then take a step in the opposite direction of the gradient, and then in the projected case, projecting down onto a convex body. So in the projected gradient descent, we have our data state X, we have our loss functions, Lipschitz constant, convex set C, and we're projecting down onto C. Okay. So in this version, I'm showing taking n squared steps, but there are many, many variants. Okay. Now, we can make a privacy preserving variant of this by adding Gaussian noise at every step as needed in order to preserve privacy of the gradient computation. So we have to choose some appropriate variants that will give us the privacy that we want. And then this is the algorithm. Once we have computed the gradient and added noise, that's an invocation of the Gaussian mechanism. And then everything else, multiplying by the step size, taking the step, all of that is post-processing. Projection, that's also post-processing. So there are no further privacy implications. Now, this is a lot of computation. Notice here that at every step, we have to go through every element in the data set to compute the gradient at that element. So that's a lot and prohibitive, perhaps. So Basili, Smith, and Takurta suggested the following alternative. They said, replace this expensive computation with the following. Privacy by subsampling. Let's choose a random Z from the data set, compute the gradient just at that Z, and then multiply by n to sort of compensate for the change in scale. Here we had n of them, here we have one, so we multiply it by n. If you do this, the scale and the expectation of your step are unchanged, but the computation now is much, much faster. We only had to compute one little gradient and multiply it by n instead of n different gradients. On the other hand, because we're multiplying by n, the sensitivity of our step has increased by n, which is huge. So how do we cope with this? Well, privacy of the subsample. So we chose Z uniformly at random. The chance of getting chosen is like 1 over n. That counters the n over here. So combining this with the advanced composition theorem, it's possible to actually run this algorithm for n squared steps, which is terrific because it yields the optimal dependence on n that's even given by non-private algorithms. So that's the first technique and application. Now, before explaining the second technique, I want to engage in a thought experiment. So this is an experiment in creative privacy accounting. Think about the following, the variant of gradient descent, which is known as noisy stochastic gradient descent with fixed sample order. So what is that? It's just like everything else, only we're handling one element at a time, not all n, but one element at a time. And it's being done in a known fixed order. Okay. Now, in the previous algorithm, it was safe to release all of the iterates, all of the theta t's. What if we don't release intermediate theta t's? So think about two steps of noisy stochastic gradient descent with fixed sample order. So what does it look like? We're going to take a gradient step using x1, and we're going to add half the noise needed for privacy for a gradient step. But we're not going to publish anything. Then we're going to take a gradient step using x2. And again, we're going to add half the noise needed for the privacy of a gradient step. And now we're going to publish this final value that we got, theta sub 2, having taken 2 steps. So the intuition here is that, well, look at the world from the point of view of x1. A step was taken. Half the noise was necessary to protect x1 was added. And then later, in some sense, the other half of the noise that was needed to protect x1 is added. So we're kind of creatively accounting here by saying, well, we could kind of cash in terms of the privacy of x1 later if we want to, after we've added more noise. And so the intuition here is that x1 is fully protected. But of course, x2 would only be half protected because we've only added half the noise we need for x2 after taking the gradient step that used x2. Right. So is this valid? Does this work? And notice that this relies importantly on keeping things secret. If we published the result after the first noise, then we wouldn't have given enough privacy for x1. So let's call this amplification by secrecy of the journey. And the bottom line is that this works, although there really is an issue with the fact that samples that are x's that are handled later, xi's that are handled later have less privacy than the xi's that are handled earlier. So Feldman et al. Give a fascinating analysis of this, and then they introduce some techniques to cope with this weakness, the fact that later elements are poorly protected. Now, suppose you wanted to take still more steps. So their analysis was applied to taking t equals n steps, but suppose you wanted to take many more steps to maybe get better bounds, better accuracy bounds. Could you do it? Well, 2 different proof techniques argue that the privacy loss levels off as the number of steps goes to infinity. So one technique involves viewing noisy stochastic gradient descent as a discretization of a continuous time algorithm with bounded privacy loss, specifically the stochastic gradient Langevin dynamics algorithm. And the other is this privacy amplification via iteration plus some techniques involving subsampling Gaussians, which we won't get into. But I'd like to say a little bit about this work. I should note that both of these analyses use the yet further relaxation, which is known as alpha epsilon Rényi differential privacy, which says here alpha and epsilon are parameters, and the requirement is that the alpha divergence, and here I'm reminding you of the definition of the alpha divergence, has to be bounded by epsilon. So this is a statement about all of the divergences for beta less than or equal to alpha down to just above 1, and it doesn't make any promises about what happens above alpha. In contrast, concentrated differential privacy has requirements for all of them. Okay. Now, suppose we have two databases, X and X prime, and we imagine two runs of noisy stochastic gradient descent for each of these. Think of X1, capital X2, capital X3 as being the random variable that describes the location of the iterate theta after the first gradient step, second gradient step, and noise additions and so on when we're running on database X. And similarly for X1 prime, X2 prime, when we're running on data set X prime. And we start with an upper bound on their distance. Some might be 0, might be 1 with some fixed upper bound on their distance. And we're going to here abuse notation and identify the random variable with its probability distribution. So starting from this metric condition, we want to draw a conclusion about the Rényi divergence between the distributions after capital T number of steps when we're running on database X versus running on database X prime. And this is an information theoretic distance which doesn't know anything about metric structure. So how can you prove this? This is the challenge. So the key definition is a hybrid distance, which is called the shifted Rényi divergence that interpolates between the metric distance and Rényi divergence. Recall the Wasserstein distance between distributions P and Q. This is the infimum over all couplings of P and Q of the maximum distance between X and Y in a draw from this coupling. Now, for fixed Z, consider the radius Z Wasserstein ball around distribution P. And let P prime be the distribution within this ball that has the smallest alpha divergence to Q. This is the Z, this distance is the Z shifted Rényi divergence between P and Q. Notice that when Z is 0, this is just the alpha divergence, and that also if we increase the radius of the ball, we can only decrease the shifted alpha divergence because we're just taking more choices into account for P prime. And if we make the ball large enough, and in fact, it's so large that it includes Q, then the shifted Rényi divergence between them is 0 because we just take P prime equal to Q. So Feldman et al. Introduce a shift calculus or an accounting system. And we can think of Z in the shifted divergence as a debt. And eventually we want to end up with Z equals 0, which will give us the Rényi divergence at time t. Taking gradient steps adds a bounded amount to the shift, sort of increasing debt, but while decreasing the shifted divergence because Z is getting larger. But in contrast, when we add noise, that's like putting money in the bank, which we can spend on decreasing the debt or the shift when we choose to spend it. And when we do, there will be some charge in actual divergence. So these are the tools that are used in the first paper. And the goal is to end up at the last step with Z equals 0 without ever going negative along the way. So how much you increase your debt when you take a step, that's kind of imposed, but how much you decide to charge for decreasing when you add noise, there's your flexibility. And remember that when Z is as large as the diameter of our convex region, the shifted distance becomes 0 since Q itself will be captured. And the work of Altshuler and Talwar exploits that last fact. After sufficiently many steps, Z will be so large that the shifted divergence becomes 0. So the proof of privacy only needs to be concerned with what happens in the final steps and after this point has been reached. And with that, thank you for your attention.
Great lecture, Cynthia.
Thank you, Ron.
Yeah, I guess